All right, so this is the third example on the assignment that we titled optimization. So what we've done so far is we've talked about our first example where we dealt with the area of the fence. The second example, so you can see our first example was the area of the fence example. Our second example was the dimensions of a maximized volume for a box given a specific surface area. The third example is the volume of a cylindrical tin can with a top and a bottom is to be 16 pi cubic inches. So I have a given volume, and if the minimum amount of tin is to be used to construct the can, what must the height in inches of the can be? So now what we're trying to find is, assuming we have some sort of cylindrical can, like so. We know this can is going to have a height and a radius. And we come up with our equations. We find out that our primary is supposed to be a minimum surface area. We are going to construct this. We know that it has a top and a bottom, so that's useful. So we find out that the surface area, don't call it SA, I'm just going to call it area of the entire thing, is going to be we have two bases that are circles, so those are pi r squared. And we have two of those, plus the surface area of the lateral portion is going to be whatever the circumference is, 2 pi r multiplied by h. The secondary equation we're looking at is the fact that we know that the volume, 16 pi, is supposed to be pi r squared h. If the minimum amount of tin is to be used, what must the height of the can in inches be? So we have some options. We can either solve for h, you do the problem in terms of r, and then move on from there. Or we could try to get r by itself. So I'm looking at the secondary equation. There's a couple things I might opt to do here. For instance, I'm noticing I can divide out a pi, leaving me with 16 equals r squared h. I'm not sure which one I want to do. It seems like it would be really easy to solve for h, but then I'm going to get the answer in terms of r. And do I really want to deal with that? And yeah, because I really don't want to have any square roots built into this problem. So I'm going to go ahead, I'm going to get h by itself actually, which seems counterintuitive. But I really like getting the h by itself because it's going to keep me from any square roots. Everything will be nice whole numbers up here still for my radicals. So wherever I see an h, I'm going to replace it with 16r squared. So then know that my area is going to be 2 pi r squared plus 2 pi r times 16 over r squared. I don't like that. I've got a product rule, maybe some quotient stuff going on. I want to simplify that. Let's call this 2 pi r squared plus 2 times 16 is 32 pi r to the negative 1. All right. All the hard work is done at this point. We just need to start working some calculus. So I'm going to take the derivative with respect to r in this question. I'm going to get 4 pi r for the first term. And for the second term, I'm going to get minus 32 pi r to the negative 2 is equal to 0. I'm going to rewrite this. I'm going to get 4 pi r minus 32 pi over r squared. I'm going to let that still equal 0. And right here I am going to take the time to make sure to note that this is in case r is greater than 0. The reason why I want to do that is technically there are two critical points here. One of the critical points that most people will find is they're going to solve for this particular critical point. They're going to say 4 pi r is equal to 32 pi over r squared. I'm going to multiply the r squared over and divide by the 4 pi. Get r cubed is equal to 32 divided by 4 is 8. And they're going to say r is equal to 2. And that's good. But as of right now, there's actually not one critical point, but two if we were to actually solve this without this piece, because remember that dA/dr is also going to be undefined at r is equal to 0. So there would be technically two critical points if I don't make this statement r has to be greater than 0. Of course, if r is equal to 0, you don't have a tin can anymore. You've got a dimensionless, one-dimensional line, and it's all sorts of problems. We don't like that. So I'm going to take this, I'm going to make a 2, and I need to figure out what on earth is this going to be. So we already know 0 won't work in this case. I'm going to do a 1. 4 pi minus 32 pi is going to be 4 pi times 1, and a 1 here, 4 by 1, 32, that should be a negative, and this should be a positive. And at first you might think to yourself, wow, that doesn't seem like that's right, we're messing up, but remember what we're looking for here. We're looking for a minimum amount. So in the last two we've looked for maximizing. In this case we want a minimum. And if this changes from negative to positive, then that fits our criteria we were looking for. We can call that a relative minimum. And because we've set our boundary here as r is greater than 0, because it makes sense for the context of the question, then what we know is that that's the only critical point. Thus, we have a minimum volume. So just like in the last problems, we have a minimum volume at r is equal to 2, I believe it was inches. Let me double check. Yes. We have minimum volume since, and we can say that not minimum volume, we have a minimum area, surface area. Just start writing vertically. Because dA/dr is equal to 0, and changes from negative to positive at r equals 2 inches, and r equals 2 inches is the only critical point on r is greater than 0. So we've proven that the minimum surface area occurs there. Have we answered the question asks what is the height of the can? We have not. We know that the height is equal to 16 now over 2 squared. Height is 4 inches. H equals 4 inches is my final response. Ladies and gentlemen, I hope that that made some sense. Be sure to come in and ask questions as you go through that. If there's anything that was messing with you, if you did not get a chance to see the previous problems, don't forget we have this example number 2 as well as this example number 1. Feel free to kind of backtrack to the time slots those were at so that you can, again, 1, example 2, you can stop it, take a look at those notes. We'll be working these problems like this tomorrow, and you will also, well, actually, no, you won't be getting your review until later. So hope everything goes well, and look forward to seeing you all then tomorrow.